So we saw Carol Svoboda's results, this in vivo calcium imaging in a mammal for the first time, 1999, right? And I've said it relied on this two-photon laser, this two-photon imaging, right? And I haven't really sort of explained much about it apart from the fact that this laser is super powerful. It uses infrared light and it sends out tiny little packets of light, little pulses, instead of a continuous beam. What's all that about? Okay, so what is two-photon? So you've learned about fluorescence before, right? And it's about you put in a high energy photon. This is what this blue light here is, and it excites an electron in the fluorescent molecule. So the energy of that photon is absorbed by the electron. Then the electron hangs out for a little bit, might lose a bit of energy via some non-radiative mechanism, right? So it doesn't emit a photon, but it loses a little bit of energy, and then it drops all the way down to the ground state. Right, so it loses the energy, and when it loses all of that energy, it has to emit a photon, right? Because the energy can't be created or destroyed, so off it goes. Now, because a little bit of energy was lost from absorption to emission, that photon comes out with a different wavelength because of quantum physics nonsense, right? Point is that the wavelength and the energy are directly proportional to each other, and so it absorbs high energy and then it emits lower energy, and that is in parallel with the fact that it absorbs a short wavelength and emits a longer wavelength. So that is one photon fluorescent, normal fluorescence for normal people. Two photon fluorescence is kind of the same, but a little different, right? Same concept. You've got an electron, you excite it to a high energy state, it twiddles around a little bit, and then it emits that energy as a slightly lower energy photon. But the trick here is, instead of it absorbing one high energy photon, it has to absorb two low energy photons. Two low energy photons that have exactly, or close to exactly, half the energy of the one photon. So basically, anything you can excite, give or take, with one photon fluorescence, you can also excite with two photons that have half the energy. So the total energy is the same, you've got to have two. But in order to do that, there's got to be two photons going through that molecule basically at the same time, which means there's got to be a lot of photons, right? Those photons have to be flooding through the tissue so that they're basically sitting on top of each other so they can go past this fluorescent molecule and hit it at the same time. And there's all this maths around exactly how close together, but it's like, basically at the exact same time. And so that is the importance of the super high power laser. Now you might say, okay, hang on, this laser sends in little pulses and then silence and then a little pulse. Well, why not just put it in as a continuous wave? Well, if you were to do that, you would boil the brain away in a second, right? In a femtosecond. That those little pulses have an immense amount of energy, truly immense amounts of energy. But because they're very, very short and separated in time, the brain can dissipate that energy without heating up at all. But if they were to come in constantly, the brain would just boil. In fact, you can do that accidentally if you're not careful. I've done that in some of my early experiments. Anyway, there's another reason why two photon is so good, right? So in order to get two photon, you have to put in two photons that are have half the energy as the one photon. So that means those photons must have a longer wavelength, because as I said, short wavelength means high energy, long wavelength means low energy. Now that puts you in a favorable range for imaging the brain. Now if you did CHP 311, you know that water, right, it likes to let through visible light. But something I didn't mention to you was that blood likes to let through infrared light. So blood is very good at absorbing visible light. So here we have the extension coefficient again, how much it absorbs. So it absorbs pretty much all visible light up to about 600. Then in the 600, 700 range, there's quite a difference between oxygenated and non-oxygenated blood, and yes, that can be used to measure neural activity, but as you go further up, you just get less and less. So the infrared is great to go through blood. Now, these two graphs are in the same unit, and so the point here is that this dip doesn't look very impressive, but in these wavelengths, the absorption of blood is far higher, right? So on this graph, the absorption of blood is at about this line, well, from here to here. So in this range around here, the absorption of blood is a much bigger problem than the absorption of water. So it doesn't matter that we've snuck up here, up the side of the absorption curve for water, i.e., water lets through visible light better than infrared, but it goes through blood way easier. So yeah, avoiding being absorbed by blood is more important. So those things all mean that traditional fluorescent dyes can be excited with these infrared lasers, and it can be done in vivo because they can pass through the tissue. So as I said, you need these extreme high density of lights, which is what these mode lock lasers do. So I sometimes like to think about this instead of timing, right? Because femtoseconds and nanoseconds is very hard for us to imagine, right? But if you imagine if you had this beam of laser light sitting there and you were to freeze time, right? What you would see is that these pulses would be 30 micrometers long, so that they are, less than the width of a human hair. But between each pulse would be a 3.5 meter gap. So that means that 3.5 meter beam of light has been compressed down into that tiny little pulse, which is where the huge powers come from. So the average power of the laser is like 3 watts, right? That's like the power of the LED at the end of your TV remote, maybe, and your typical incandescent light bulb is 60 watts, 100 watts. So that sounds pretty unimpressive. But the peak power, the power in those little pulses is 300 kilowatts, right? Which is not quite, you know, the output of a power plant, but it's closer to that than anything that's going on in your home. Okay, if you were to try drawing 300 kilowatts with anything in your home, not only would you pop every circuit breaker on your board, you'd probably pop some circuit breakers down in the street as well. So it's a lot of power snuck into that tiny little packet. Now, because you need this massive density of light, only a very small point gets enough photons to be excited, right? So here we see typical epifluorescent confocal style of setup where we have excitation light coming through the objective of the microscope. It's being focused down onto the focal point, right, and then it spreads away. And you can see that it's exciting this tissue the sort of the whole way. Yes, it's brighter here, but there's stuff out here. So this is the out of focus light that we don't want, right? Because we want to be focusing on one point and only looking at that point. But here it is in a two-photon. You can see there's just a tiny wee pinprick in the middle because everywhere else there's just not enough photons for two-photon excitation to ever happen. So what that means is all of the light that is coming off the tissue, all of the emitted light, you can just absorb it all. Unlike in one photon imaging, where you need to have some technique to throw out light that is coming back from the sample if it's out of focus. So in confocal, that's the pinhole. Um, and what that means is that you can just absorb, you can just take all of the light. Doesn't matter where the light comes from, you can take it, and it came from your focal area.